Okay, so in the last class we discussed discrete time systems in the frequency domain, and in this class let us consider a couple of examples. Okay, let me call example number 1. Suppose you have an x of n which contains two sinusoids. Let me call A cos of omega 1 n plus B times cos of omega 2 n. Okay, so the frequencies are omega 1 and omega 2. The signal x of n is not necessarily periodic. Is this statement correct? In digital signal, even if it is cosine waveform or sine waveform, okay, even if it is in sine or cosine representation, is not necessarily periodic. For periodicity, we said omega 1 by 2 pi must be a rational number. Then only you can say it is a periodic function. Similarly, omega 2 divided by 2 pi must be a rational number. Otherwise, you cannot say that sinusoid is a periodic sinusoid, periodic signal. Okay, and the denominators of omega 1 and omega 2 must have, if they are periodic, then the periodicity of the sum is the LCM. You know how to do this. Suppose you have two signals. Okay, so let me call this is x1 of n, and there is another signal x suffix 2 of n, and if we want to pass omega 1, right, and reject omega 2, that is, the condition should be omega 1 is greater than 0, right, but it is less than omega c. Okay, so omega 1 must be less than omega c. See, omega c is the cutoff frequency, so that between 0 and omega c, omega 1 should lie there in order to pass this guy. So this is my pass band. Right, and then this omega c must be less than omega 2 on the frequency axis, and this omega 2 is less than pi. Therefore, in the frequency axis, if you look at, this is 0 and this is omega c. In between somewhere your omega 1 lies, because I want to pass omega 1 and omega 2 should be rejected, and this omega 2 lies between omega c cutoff frequency and pi. Pi is the highest value. Okay, therefore 0 less than omega 1, right, less than omega c, less than omega 2, because omega 2 must be stopped, and then pi. Okay, therefore this condition specifies that it is a low pass filter. See, you are passing the frequencies from 0 to omega c, in that your omega 1 lies. Okay, therefore 0 to omega c is our pass band, right? So our omega 1 lies there between 0 and omega c. So it could be in the transition band. Sorry, omega 2 is greater than omega c, and omega 2 could be in the transition band or in the stop band. Now we can design filters such that the transmission at omega 1. Now what would be your y of n? Suppose if I feed the signal in this filter, a times cos of omega 1 n plus b times cos of omega 2 n. What will I get in the output? My y of n contains only one component. What is that component? A times cos of omega 1n only, plus some phase angle that I will write down. Okay, so if you pass the signal through this filter, this filter let me call LTI system. Okay, it is an LTI system. Now if I feed the signal A cos of omega n plus B cos of omega 2n to an LTI system, the magnitude would be modified by how much? H of e to the j omega 1, and the phase would be modified by, and phase angle of h of e to the j omega 1. Therefore I cannot write like this. I should have written as the magnitude A. This A will come as it is, but because of this LTI system, the magnitude is modified by magnitude of h of e to the j omega 1 and cos of omega 1n plus some angle. What is that angle? H of e to the j omega n. That's it. Okay, so do you see how we are writing the response? Okay, all you have to do is find the frequency response of the system. This system, you just to find out what is the frequency response. Then the output we can write directly, that we already discussed in the last class. So this cosine of omega 1n will be affected in magnitude by how much? This much. Okay, by magnitude of h of e to the power j omega n at omega is equal to omega 1. Its angle will be shifted by this much. Okay, so this is due to the first component. What about the second component? Similarly we can write plus b times magnitude of h of e to the j omega 2, it is at the frequency omega 2, times cos of omega 2n plus its angle at the frequency omega 2. Okay, so that's how you will write the output of an LTI system. Now all that I have to find now is we have to choose a system in such a manner that magnitude of h of e to the j omega 1 should be approximately equal to 1, because I need to pass it through the output ideally. Okay, therefore ideally I can make it h of e to the power j omega 1 must be approximately equal to 1. I want to pass it through the filter. And the second component I don't want. How can I stop it? Make the response to 0. Therefore, the second component will be disappeared. So, you make h of e to the power j omega 2 magnitude is approximately equal to 0, so that the second component will be disappeared. Right? So, the magnitude of h of e to the j omega 2, right, should be approximately equal to 0. That's how we can do the low pass filtering. Now this is a general concept. Now let us take a specific example, and to bring variety into experience. Okay, so let's say we require a high pass filter or band pass filter, doesn't matter. Let's say we require a high pass filter. So x of n is equal to a times cos of 0.1 n. Now instead of omega 1 I have written 0.1 here, plus b times cos of 0.4 n. Okay, and here a and b are constants. Okay, we need not bother about them. Okay, let us take a is equal to 1 and b is equal to 1. So just leave it. Okay, therefore I can write x of n Generally we don't bother about these constants. Cos of 0.1n plus cos of 0.4n. Now is this periodic? No. Okay, this is not periodic because 0.1 divided by 2 pi can never be a rational number because pi is an irrational number, so it is not periodic. Okay, this is not periodic. Okay, pi is a well-known irrational number. Okay, don't say it is a rational number. Okay, people will write 22 by 7. Okay, this is approximate value, so don't say pi is equal to 22 by 7. Okay, so pi is a well-known irrational number, it's not a rational number. Similarly, 0.4 by 2 pi is also not a rational number, it is irrational. Therefore x of n is not periodic. Now the condition is, what is the condition? This we want to retain. Okay, so this is to be retained. Omega 0.4 must be retained and this 0.1 must be rejected. So we need to design a filter in such a way. Like 0.4 is higher than 0.1, so 0.1 must be rejected and 0.4 must be passed through the filter. So that means higher values are passed and lower values are stopped. So what kind of filter is this? High pass filter. Okay, see in the frequency axis, if you look at, let's say this is 0.1 and this is 0.4, and 0.4 I should not pass, so I should have 0 voltage or 0 amplitude, but 0.4 must be passed up to pi. So therefore what type of filter is this? High pass filter. Okay, therefore we want to make it h of e to the 0.1n magnitude must be equal to 0 or approximately equal to 0, and h of e to the 0.4n is approximately equal to 1 because I want to pass this guy, this frequency I want to pass it through the filter. Let's see if we can satisfy this. Okay, how okay, let us design, okay, a simplest possible kind of filter to satisfy this condition. To start with, let it be FIR of length 3. Okay, finite impulse response filter of 3. Okay, and I am choosing this arbitrarily. You can take 5, you can take 4, you can take 6, it's up to you. But to make our life simple, I am choosing, the length of the filter is 3. Okay, I could also choose 2 also, length 2. But let's say, okay, suppose that my h of n, my impulse response is alpha, beta and alpha, and this is the this is n equal to 0. Okay, see I recover 2 degrees of freedom because I recover 2 constants, okay, alpha and beta, which are to be adjusted to satisfy these two conditions. That means at point 1 the magnitude should be equal to 0. At point 4 the magnitude should be equal to 1. That's why I chose 2 constants. What is h of e to the j omega? It is the DTFT, discrete time Fourier transform of h of n. H of n is the impulse response, h of e to the j omega is the discrete time Fourier transform of DTFT of h of n is equal to h of e to the j omega. Okay, so h of n is given, so we can find out h of e to the j omega. So therefore this is, we know the formula, so straight away I can write down the result here. H of e to the j omega is equal to alpha times what is the h of x of n is given, then how do you find out its discrete time Fourier transform? X of e to the j omega. What is the formula for x of e to the j omega? Summation of n is equal to minus infinity to plus infinity x of n e to the minus j omega n. Recall this formula. Substitute the n value. So here n value is 0, here n value is 1, and here n value is 2. Okay. Therefore, this is summation of h of n e to the minus j omega n, and I have only 3 values. So therefore n is equal to 0 to 2. Expand this, h of 0 times e to the 0 plus h of 1 times e to the minus j omega plus h of 2 times e to the minus j 2 omega. What is h of 0? Alpha. What is h of 1? Beta e to the minus j omega plus h of 2 is again alpha e to the minus j 2 omega. Okay, so now you can do a little bit manipulation in this. So what I can do is I can pull out e to the minus j omega commonly outside. So in between I have beta plus alpha times e to the plus j omega plus alpha times e to the minus j omega. I can write like this. Okay, if I take e to the minus j omega out, e to the minus j omega beta plus I can combine these guys, alpha times e to the j omega plus e to the minus j omega, and then you divide by 2 and multiply by 2. So this is going to be e to the minus j omega multiplied by beta plus 2 alpha cos of omega. Agreed? So it is very tempting now to say that the magnitude of h of e to the j omega is this quantity. No, this is not magnitude. Okay, not necessarily. Why? Because you must be very careful in this. Okay, this part is real, but it doesn't mean that it cannot go negative. Okay, so this cos of omega can be positive as well as negative. So this is a step where you can falter throughout your journey of digital signal processing. Wherever a real quantity is given, it can be positive as well as negative. Both have to be respected. So the negative sign have to be respected by including an angle of pi in the angle of e to the minus j omega. So the angle of h of e to the j omega is minus omega as long as this guy is positive, as long as this guy is a positive quantity, and this is minus omega plus pi whenever this quantity changes from positive to negative. So this is positive, negative. Whenever it changes, then this is the phase angle. So whenever it becomes 0, there is a transition of phase by an amount how much? Pi. Okay, so now let us suppose that we aim at beta and alpha in such a manner that that this quantity will remain positive. Let us assume this quantity will remain positive. We need to design a beta value and alpha value such that this quantity remains positive. And if the final result does not justify it, then we will go back. Okay, so initially let us start with the whole quantity is positive. Let me write down here beta plus 2 alpha cos of omega, right, e to the j omega. initially what I am saying is, let us assume that this quantity is positive. So if this quantity both positive means, let us assume beta also positive and alpha also positive. In case once you solve this or design this, and finally if alpha and beta are not positive, then we go back and do something else. So this is the engineer's way. It doesn't it does not quite start with a rigorous mathematical formulation and so on, because then he gets lost in the mathematics. So you have to keep your eyes towards practical situations. So what I want is the following. So this h of e to the j omega is equal to e to the minus j omega times beta plus 2 alpha cos of omega, right? So this is a general equation we derived. Now one second. Fine. Now what is the condition that we derived here? Look at here from the given problem. Look at here. At 0.1 n, my magnitude of h of e to the j omega must be 0. At 0.4, magnitude becomes 1. Therefore, I have two frequencies and two values. Then I'll get two equations. Okay. So in this, you substitute omega is equal to 0.1 and omega is equal to 0.4. So therefore, h of e to the j 0.1 n magnitude is equal to 0, e to the minus j omega. If you take magnitude, then this guy will go, e to the minus j omega will go, beta plus 2 alpha cos of 0.1. Okay, this magnitude must be equal to how much? 1. Therefore, beta plus 2 alpha cos of 0.1 is equal to 1 or 0. Sorry, it is 0. I should not pass 0.1. 0. Similarly, h of e to the j times 0.4 n, if you take magnitude, then this must be equal to 1. So magnitude of e to the minus j omega, let's say this is 0.1. 0.4 beta times 2 alpha cos of no, why did I put n here? I'm sorry, the n will not come here. 0.4. What did I do here? I made it correctly. I'm sorry, here also I did a mistake. This n not supposed to come. Okay, this h of j omega, n is a time parameter. Okay, in the frequency domain you should not get n. Okay, that's a silly mistake. .4 magnitude must be equal to 1. Therefore, beta plus 2 alpha cos of 0.4 is equal to 1. Let's say this is equation number 1, equation number 2. And you subtract one from the other and find alpha very easily. And you look at here, this 0.1 and 0.4 are in radians. Okay, cos of 0.1 and cos of 0.4 can be found out from the tables or by using scientific calculator, and therefore one finds that the alpha and beta values. Okay, so if you do the calculation, alpha is equal to minus 6.76195 and beta is equal to 17.456335. Okay, now with these values you can verify that beta plus 2 alpha cos omega remains positive between 0.1 and 0.4. Okay, that's all that we are concerned with. Okay, it remains positive. Now if you look at I have chosen 1 2 3 4 5 digits here after decimal, and here 1 2 3 4 5 6 digits after the decimal. Okay, so I have chosen arbitrarily, but it depends on how many bits are required to represent. Sometimes you may require only 2 bits, 2 digits, sometimes 3 digits. It's up to you. Okay, it is the requirement of the application. Okay, how accurately you want to represent it. Okay, and moreover the amount of hardware and software and so on. So if you have a limited amount, for example, if you have a limited amount of cloth, then you have to decide, okay, how many shirts can be made out of it, or how many pieces of dresses. You have either an 8-bit or a 16-bit of hardware. If it is a software, let's say you can go up to 32 bits. So you decide the number, that is the precision which can be represented by as many bits. For example, if it is an 8-bit number, you should not truncate after the first decimal. Okay. On the other hand, if it is a representation in floating point, then you can use more decimals. Floating point representation, you can use more decimals. These are elementary things from your digital logic design. Therefore, it is decided by the amount of money that you wish to spend. That is amount of investment. How much money you are ready to pay it. Now, obviously, after you found out alpha and beta, the system is now known. Now, what would be its difference equation? For example, h of n is given, right? What is h of n? Alpha, beta and alpha. This is your h of n. Now, I would like to write in terms of difference equation. So how can I write it? Do you remember that? Your y of n is equal to alpha times x of n plus beta times x of n minus 2 plus n minus 1 alpha times x of n minus 2. How did I get this expression? X of n is given to the system and this is my h of n. What is y of n? Y of n is the convolution of x of n with the h of n. Okay, so x of n convolved with the h of n. What is h of n? H of n is alpha, beta and alpha. This is n is equal to 0. So how can I represent h of n in terms of, this is the one way of representing, but the proper way of representing h of n would be alpha times del of n, because the sample is sitting at n is equal to 0 with a magnitude of alpha, plus beta times del of n minus 1 plus alpha times del of n minus 2. So alpha times del of n plus beta times del of n minus 1 plus alpha times del of n minus 2. Now convolve x of n with del of n, you will get a x of n. Therefore delta times x of n, alpha times del of n. Convolve x of n with del of n minus 1, that is del of n minus 1. This, recall this property from your signals and systems course. And beta plus convolve x of n with del of n minus 2, again alpha times x of n minus 2. That's how you write your y of n. So straight away I wrote here. So this is my y of n. And you can implement this y of n with the 2 multipliers. Do I need 2 multipliers or 3 multipliers? Only 2, because here also I have alpha and here also I have alpha. So I can use only one multiplier. Don't use 2 multipliers. Okay, because x of n and x of n minus 2 can be added together before you multiply by alpha. Essentially you are reducing the number of multipliers. Okay, so reducing the number of multipliers is an extremely important criterion in the realization of a DSP. Okay, how will you realize it? X of n okay, and give it to a delay, and after that put one more delay, okay, and this point, what is your signal? X of n minus 1. You put a multiplier, and the multiplying constant is beta. So what is the thing you will get here? It is beta times x of n minus 1, and then you put a summer here. Here in this point you got x of n, and in this point what is the thing? X of n minus 2, because delayed by 2 samples, here one delay and here one delay, 2 times. So in this place you will get x of n plus x of n minus 2, and you put a multiplier now, sorry, alpha. Now in this point you will get alpha times x of n plus x of n minus 2, and then give it to the summer. Okay, so this is your y of n. So y of n is essentially this equation. So that's how you implement. Now look at, I need only 2 multipliers, multiplier 1 and multiplier 2. So reducing the number of multipliers in an multipliers is an extremely important criterion in the realization of a DSP. Now if you notice, if the processor is not an FIR, it is IAR, then you know it can be written down in the form of a difference equation like this. Okay, so in general the difference equation can be written as follows: y of n plus b suffix 1 y of n minus 1 plus etc plus b suffix n, capital N, y of n minus capital N is equal to a naught times x of n plus a1 times x of n minus 1 plus etc a suffix capital M x of n minus capital M. Okay, so this is the general representation of an LTI discrete time system. General representation of a linear time invariant discrete time system. Okay, and this representation can be FIR or it can be IIR, infinite impulse response. Okay, but the most general representation is this one. And then you can write the frequency response. For this you can write down the frequency response h of e to the power j omega. How will you write down? By taking dTft. Okay, so if you take dTft, then y of n becomes y of e to the power j omega, y of n minus 1 becomes what? E to the minus j omega, y of e to the j omega, and so on and so forth. Similarly, x of n becomes x of e to the power j omega, x of n minus 1 becomes e to the minus j omega, x of e to the power j omega, right? And etc. Like x of n minus capital M has the dTft of e to the minus j capital M omega times x of e to the j omega. Like that you can write. And then we know this h of e to the power j omega is equal to discrete time Fourier transform of the output divided by discrete time Fourier transform of the input. You can do it, it's very simple, straightforward procedure. So if you do that, this one, okay, maybe I'll write down for you here. So this is y of e to the j omega plus e to the minus j omega, y of e to the j omega plus etc, right, e to the minus j n omega, am I right? I'm sorry, I forgot the multiplier. This is b1 and here bn, y of e to the j omega is equal to a naught times x of e to the power j omega plus a1 e to the power minus j omega times x of e to the j omega plus etc plus a suffix capital M e to the minus j omega capital M times x of e to the j omega. Now I can take y of e to the j omega commonly outside in the left hand side. So y of e to the j omega you take commonly outside, 1 plus b1 times e to the minus j omega plus etc b suffix n e to the minus j omega n is equal to, you take out x of e to the j omega commonly outside, inside a naught plus a1 e to the minus j omega, am I right? Yes, plus etc plus a suffix capital M e to the minus j omega capital M. Now you write down y of e to the j omega divided by x of e to the j omega is equal to the numerator a0 plus a1 e to the minus j omega plus dot dot plus a suffix m e to the minus j omega m in the denominator, 1 plus b1 e to the minus j omega plus etc plus b suffix n capital N e to the minus j omega n. And what is this? As I said, h of e to the j omega. Therefore h of e to the j omega a0 plus a1 e to the minus j omega plus a suffix m e to the minus j omega m divided by 1 plus b1 e to the minus j omega plus etc plus bn e to the minus j omega n. And if you notice in this representation, what is this? This is b naught. Here in the numerator I have a naught, but in the denominator instead of b naught I made b naught is equal to 1. And this is the discipline that we try to inculcate. So b naught is always 1. If there was a b naught, we would have divided by b naught all through. Okay, in case if this value is not 1, then some other value, then divide the whole expression by that value, so that you make the coefficient of y of n is equal to 1. Okay, so whenever you write the general expression, in that expression you should always make sure that coefficient of, this is the nomenclature that we will follow. Okay, coefficient of y of n must be made to 0. This is a discipline that we try to inculcate. Okay, because of that coefficient of y of n is 1, I got 1 here. Okay, so this representation in general, the form of the frequency response, this h of e to the j omega is called frequency response, and in general it represents an IIR system. Okay, there is no reason why it cannot represent an FIR system also, because there may be pole zero cancellation. Okay, now this expression can now be generalized in terms of Z transforms. Okay, so I can write down this expression in terms of Z transform, and we know the relationship between the Z transform and the discrete time Fourier transform, right? So far we have considered the representation of the discrete time systems in the omega domain. Okay, so far we have considered the representation of the discrete time systems in the omega domain. How will you get this omega domain? By taking dtft, and there is no reason why you cannot Z transform and generalize this h of e to the j omega. Okay, you can generalize this h of e to the j omega as h of z also. Okay, so that is, instead of taking dtft, we can also take a Z transform, provided the Z transform exists. Okay, like you take this expression, and here you know this y of n, if you take Z transform, you will get y of z. Y of n minus 1, z to the minus 1 times y of z, and this one z to the minus capital N y of z, and here this becomes x of z, and this guy becomes z inverse x of z, and this becomes z to the minus capital M times x of z. Again you can do the same kind of thing, and you'll get finally h of z. Okay, so you can write this one as h of z is equal to, in the numerator, a0 plus a1 z inverse plus etc plus a suffix capital M z to the minus capital M divided by 1 plus b1 z inverse plus b suffix n z to the minus n. Okay, so one can write in the Z domain also. Now let me write this numerator polynomial as p of z, and the denominator polynomial as q of z. Therefore in general h of z is numerator divided by denominator. So it would in general be of the form of a rational function, ratio of two functions, right, which is the ratio of polynomials in z inverse, not in z. Okay, so this is the numerator is a polynomial in z inverse, and denominator is also a polynomial in z inverse. So when you talk of h of e to the j omega, okay, suppose we want to find out the frequency response of h of z, what will you do? Then z will be simply replaced by what? E to the j omega. Simply put z is equal to e to the j omega, provided the ROC of h of z, okay, includes the unit circle. Otherwise the DTFT cannot exist. Okay, if not, then you cannot do it. Okay, fortunately most of the systems that are of our interest can be treated by both Z transform and discrete time Fourier transforms. Okay, however now there is a change in nomenclature. CLATURE, NOMEN CLATURE, nomenclature. So there is a change in nomenclature. This h of e to the j omega, how do you call? H of e to the j omega is called frequency response. Why is it called frequency response? Because h of e to the j omega gives spectrum. Okay, this guy gives spectrum, frequency versus magnitude, right, in terms of it gives a spectrum in terms of actual omegas. On the other hand, h of z, we must give a name to this. Okay, this is simply called the transfer function. This is called a transfer function, because you can see it is also a ratio of y of z divided by y of z and x of z. H of z is the ratio of y of z and x of z. It's a transfer function. Okay, and x of z is transferred to the output. Okay, so why is it called transfer function? X of z, you have a system and the input is x of n. In the z domain it is x of z. Output is y of n. In the z domain it is y of z. So x of z is transferred to the output, that through this h of z, right? So y of z is equal to h of z divided by multiplied by x of z. Therefore x of z is transferred to the output through this h of z. That is why this is called a transfer function. It is transferring x of z to y of z. Okay, and one should remember that the z domain transfer function and this frequency domain frequency response are intimately related, provided both of them exist. Both of them exist. Okay, now let us take one more example. Okay, if you take the m point moving average, this is the example that we are taking repeatedly. M point moving average system. Now how do you write m point moving average system? Which is equal to 1 over m summation x of n minus k, where k goes from 0 to m minus 1. Okay, see, you are including the samples from k is equal to 0 to m minus 1. Therefore total number of samples are m number of samples. So this is called a m point moving average system. Now in order to find out h of z, now the question is find its frequency response h of g omega, or you can find h of z. So how will you find out for this? Okay, so once again, it's a pretty straightforward method. You can do this. For this, in order to find out this h of e to the j omega, I need to find out first h of n. Once I know the h of n, then I can take dt of t, and then I will get h of e to the j omega. So how do you find out h of n from y of n? This already we did in one of the previous class. Okay, if you recall the previous lecture, then you will get h of n is equal to 1 by m del of n plus del of n minus 1 plus etc. It's very simple. Okay, see, you have the discrete time system, discrete time LTI system. If you give x of n, what is my output? Output is 1 over m summation of x of n minus k, where k is equal to 0 to capital M minus 1. You take the same system, same discrete time LTI system. Instead of x of n, you give del of n. Why? Because I need impulse response, the response due to impulse function. Therefore, my h of n, here my output is y of n, and here my output is h of n, because the input is delta n, del of n. So the same function, but replace x of n by del of n, that's all. See, the x of n is modified in this manner. Similarly, the del of n will also be modified in the same manner, but instead of x of n, I will be having del of n. Therefore, 1 divided by m summation del of n minus k, k is equal to 0 to m minus 1. Now expand the summation, 1 over m del of put k is equal to 0, del of n plus del of n minus 1 plus etc. plus del of n minus capital M plus 1. Okay, This is my h of n. Now what is del of n? Del of n is equal to 1 when n is equal to 0. What is del of n minus 1? Which is equal to 1 when n is equal to 1. What about this guy? It is equal to 1 when n is equal to m minus 1, right? Therefore I can write this as 1 divided by m, 1, 1, etc. 1, and this is n is equal to 0. Or I can say 1 over m, 1 over m, etc. 1 over capital M, and this is n is equal to 0. What is this? Impulse response. Now from this I can find out h of z. What is h of z? Summation of n is equal to minus infinity plus infinity h of n z to the minus n, small n. And now the limit is from 0 to capital M minus 1. H of n. What is h of n in this level? In this length, 1 by m z to the minus n. Anyway, 1 by m is constant. You can pull out of the summation. In between you have z to the 0 plus z inverse plus dot 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 plus z to the minus m minus 1, minus of m minus 1. It's a finite sum, okay? So you can use a finite sum formula and you can find out the answer. Okay, it is a geometric series. Therefore it's a geometric series. The z transform exists because the summation is finite. So what is the finite sum formula? H of z is equal to 1 over capital M, 1 minus e to the sorry, not e to this, it is z to the minus m divided by 1 minus z inverse. Now look at here, it's a rational function because I have the numerator polynomial and denominator polynomial. But this guy represents an FIR system because where is the pole? The pole is at z equal to 1, and this z equal to 1, the pole cancels with 0 at z equal to 1. How? The numerator I have 1 minus z to the minus m. Okay, now this guy has how many zeros? How many zeros? There are m number of zeros. Okay, this guy has capital M number of zeros. All are located at 1. Okay, m zeros. All the zeros are located at 1. So how will you find out the 0? 1 minus z to the capital minus m is equal to 0. Now if you put a z value, what is the z value? Z is equal, because I need to get this one. When will I get this? When will this condition satisfied? That is, substitute z is equal to e to the j times 2 pi. Therefore 1 minus 2 pi by capital M. Okay, when z to the minus m is equal to j 2 pi, then e to the j 2 pi is 1, 1 minus 1 is 0, right? 1 minus 1 is equal to 0, 1 minus e to the j 2 pi is equal to 0. So instead of e to the j 2 pi, I am substituting e to the j 2 pi by capital M and multiplied by minus m. Okay, so since we have m roots, the roots are, what are the roots? The roots are e to the j 2 pi k divided by capital M. What is the k value here? K is equal to 0, 1, 2 up to m minus 1. Okay, I cannot simply put e to the power of j 2 pi. I will get only one pole, but I need m number of poles. That is why we are introducing this m and this m. And this m I am replacing by k. Okay, it can take 0, 1, 2, 3 up to m minus 1, k number of poles, k number of zeros. If you substitute k is equal to 0, what will you get? You will get z to the 0, e to the 0 is 1, therefore 1 minus 1, 0. So the numerator and the denominator polynomial will get cancelled. Okay, it has just one pole at z equal to 1. And you notice that k is equal to 0 gives z equal to 1. So there is 1 0 at z equal to 1, and this 0 cancels with the pole at z equal to 1, because I need 1. I have 1 minus z to the minus m divided by 1 minus z inverse. So one pole, this numerator has m number of poles. Out of this m number of poles, one pole which is located at m number of zeros, and this has only one pole, and the pole is located at 1, z is equal to 1. And here all the zeros are located at z equal to 1. Therefore, no, it's not located at z equal to 1. There are, when you substitute, k is equal to 0 in this expression, you'll get z is equal to 1. I am sorry, okay, I told you wrongly. Okay, how many zeros? M zeros, but not all of them sitting at in one place. Okay, so it may sit in different places. But the numerator polynomial has how many zeros? How many zeros? Capital M number of zeros. Out of capital M number of zeros, 1 0 is sitting at z equal to 1. The 0 which is sitting at the location z equal to 1 cancels with a pole which is sitting at z equal to 1. So there is a pole 0 cancellation. It may slightly confuse you. So let me tell you one more time. 1 minus z to the minus m divided by 1 minus z inverse. Now in the denominator I have a pole. In the numerator I have a 0. How many zeros? Capital M number of zeros. The denominator, how many poles? Only one pole. Okay, where does this pole locate? This pole is located at z is equal to 1. In the numerator, I have m number of zeros. Out of this m number of zeros, 1 0 is sitting at z equal to 1. Therefore, the 0 which is sitting at z is equal to 1 will cancel with a pole who is sitting at z equal to 1. That's what I am trying to say here. So there is a pole 0 cancellation. And still the system is FIR after the pole 0 cancellation. Okay. So therefore, to determine the frequency response, which we already done, okay, and discussed, what you do? This is my h of z. To determine the frequency response, one has to replace z by what? Z is equal to e to the j omega. Okay, and carry out the rest of it. Okay, so this is equal to 1 minus e to the minus j omega m, and the denominator 1 minus e to the minus j omega, right? So here what you do? You take e to the j omega m by 2, then here minus j omega m by 2 plus e to the j omega m by 2 minus e to the minus j omega capital M by 2. Am I right? In the denominator, here you take e to the minus j omega by 2, here e to the j omega by 2 minus e to the minus j omega by 2. Am I doing correctly? Yes. Now this becomes multiply by 2j in the numerator and denominator 2j. Here also multiply 2j and divide by 2j. And this is going to be sine of omega by 2, and the numerator is going to be sine of omega m by 2. So e to the minus j omega capital M by 2 times e to the plus j omega by 2. And anyway, this 2j and this 2j will get cancelled. So the numerator sine of omega capital M by 2. The denominator sine of omega by 2. Okay, now you can simplify this. This is my frequency response. You can do this. It's a pretty straightforward algebra. Okay, now when you express the transfer function let's say transfer function is h of z. When you express a transfer function, let's say p of z in the numerator and q of z in the denominator, okay, the zeros of q of z, when you write q of z is equal to 0, this will give you poles. Okay, the zeros of q of z are of course the poles of the system, and if you equate p of z to 0, and this is gives the zeros of the system. When you equate the denominator to 0, you'll get certain roots, and those roots are called the poles of the system. Equate the denominator to 0 and solve the numerator polynomial, and you'll get the solution, and those roots are called zeros of the system. So you have essentially two polynomials. Take the denominator polynomial, equate to 0 and solve it, and you'll get roots, and those roots are called poles of the system. Similarly, take the numerator polynomial and equate to 0 and solve the numerator polynomial. You will get roots, and those roots are called zeros of the system. And you know how to represent them in the z-plane, right? Zeros are represented by small circles like this, and the poles are represented by crosses. But the important point is that if qi is one of the poles, let's say this is q1 and q2 and this is q suffix I, okay, qi is one of the poles, then this magnitude of qi must be bounded by unity. What is the logic? Because the impulse response will be of the form q suffix I to the n times u of n. It's a right-sided sequence, and if qi magnitude not bounded by unity, then it grows without limit. Therefore, the magnitude of the poles must be less than 1. Otherwise, the poles is in the form of q to the n. In case if it is 1.5, then what is going to happen? 1.5 to the n. If n is a value, right? N can take 1, 2, 3, 4, 5 and keep on goes. Therefore, this value increases indefinitely, and you will get a unstable system. So, in order to get a stable system, this pole must be less than 1. Magnitude of the pole must be less than 1. Okay, not that unstable systems are not useful. Okay, don't come to the conclusion that unstable systems are not useful. Okay, we do require unstable systems. Where do we need the unstable system? Okay, don't come to the conclusion that no, unstable systems are not useful. Okay, not that unstable systems are not useful. Unstable systems we do require for oscillation. If you want to make a digital oscillator, then you do require an unstable system, but not for any other purposes. So this qi, the poles must be inside the unit circle. Okay, the radius is unity. So it is a repetition of what we have done. Okay, I mean what we have studied earlier. So I think let me stop the discussion at this point, and we will continue our discussion on filtering in the next class. Okay, we will take some very simple examples of filters. I mean simple digital filters. Okay, digital low pass filters, digital high pass filters, digital band pass filters, digital band stop filters, that we will discuss in the next class. Thank you.